I might want to go over that. Nada. Okay, very good. So I think we can get started. So I will start with these lectures. My goal is to tell you a little bit about some recent efforts in trying to solve a four-dimensional gauge theory, in this case, planar n equals 4 super Young Mills. And in particular, I will focus on a particular class of observables that we will describe soon. Now, there is a lot I could say in terms of motivation for trying to understand a solution to a gauge theory. I think the best motivation is just that we can do it, and it's standing there as a puzzle and teasing us and telling us, please solve me. And of course, we can't just ignore it, and we have to solve it if we can. But there are other kind of motivations that we could add to this more fundamental one, such as trying to see if having a solution of a gauge theory can give us some hints or can tell us a little bit more about some questions that otherwise we would have a very hard time developing some intuition for, or understanding what exactly could be going on, or perhaps we have some guesses, but we want to make sure that those guesses are reasonable, and so on. So concerning, say, scattering amplitudes, let me give you a few examples of some things that might eventually defy our intuition and that we might want to have an explicit solution at any coupling in order to be able to understand them. For example, one basic question we could ask is, suppose I take a scattering amplitude, okay, say a 6-particle one, and I consider a subset of momenta, so say some p subset, and I ask, how does the amplitude behave as this subset of momenta go to 0? So I take a subset of momenta, and we ask what happens as this subset of momenta go to 0. So as Freddy, I think, will tell you at some point, say if we have 3-level scattering amplitudes, we know very well what happens. The amplitude factorizes into 2, which you can think that if a subset of momenta becomes on shell, then you can have the probability, you can have a particle becoming on shell in the middle and propagating for a very long time, and this leads to a factorization of the amplitude. What happens if I really manage to solve the theory and ask myself what happens at finite coupling, say? Is there a singularity still there? Is this singularity softened and it becomes not a pole but something else? Does it disappear at all? How should we think about this in generic theories with massless particles? A similar question we could ask is, suppose I take a scattering amplitude and I take, say, 2 legs to become collinear. So I take the momenta of particle n plus 1 to become parallel to the momenta of particle n. Okay? And this is, again, another example of a topic that is very well studied at weak coupling. People understood at weak coupling what happens, and basically what happens is what you see in the picture. If you are sitting where Tom is, you cannot distinguish these 2 lines from a single gluon, and you think that the amplitude becomes the amplitude of n gluons, where the energy of the nth one is just the sum of the energies of the other 2. And there might be some splitting functions and so on that people worked out. But suppose we want to ask, how does it behave, for example, as we take the coupling to be very large, for example? Is it the same as what our intuition from perturbation theory tells us, or could there be some interesting new physics developing, again, because the notion of particle as we increase the coupling becomes more and more diffuse? This is another question we might want to ask. Perhaps a more pragmatic question that we might want to ask, a third question we might want to ask, is, for example, what are the systematics of high energy expansions of scattering amplitudes? Okay? So suppose we are doing high energy, and when we are doing high energy, typically we imagine that we have some particles flying very fast, and then there is all this picture that to leading order, they throw a bunch of gluons at each other, and sometimes we sum this type of diagrams. This is what is often called summing the leading logs contributions. You just have a bunch of particles, and they throw a bunch of gluons at each other, but don't change their trajectory. This is typically the leading order, in some cases at some high energy processes. But then very much less is known about what is the form of the corrections as we systematically try to develop some systematic expansions around high energies. And this is another example that if we compute scattering amplitudes in n equals 4 at any coupling, we can then study these limits and see what are the subleading terms and how should I organize my expansion, perhaps in a general gauge theory. It's another kind of very pragmatic question. A more philosophical one concerns these gauge gravity dualities. So suppose we start with some scattering of gluons, like Freddy was saying, something at weak coupling, say when we have these 5 gluons or 6 gluons, this example that Park and Taylor simplified it at 3 level. And this is, at weak coupling, it's a process which is a very 4-dimensional process. You just have a bunch of gluons in 4 dimensions, they interact with a vertex in 4 dimensions, everything happens in 4 dimensions. But we know, or we believe, that according to ADS-CFT, the same process at strong coupling has a very different description, where we send a bunch of particles. Okay, I said 6 particles, so I have to draw 6 particles. And there is some kind of minimal surface. Okay. There is a minimal surface that ends on this path. You can finish the surface. I'm not going to try. It will be a disaster. So we have some kind of minimal surface which does not live in 4 dimensions. It lives in de Sitter. It lives in 5 dimensions. There is an emergence of an holographic direction. And the dynamics of these scattering amplitudes at strong coupling is better described by this dynamics of these surfaces, of these strings that emerge in 1 higher dimensions. And then a very important question is, how does this work? What is the dynamical mechanism by which gluons become some other degrees of freedom, by which we get an extra holographic direction, and by which the degrees of freedom reorganize themselves, and we go from gluons all the way to strings? Okay? It's, of course, an important question that we would like to have a better understanding of. And, of course, this idea that we have some kind of surface, even at weak coupling, we can start seeing, if I start doing many, many loops, but planar loops like this, which can be drawn on a plane, indeed, if I put many, many, many loops, it starts to look like a surface. But then we don't want a cartoon. We want something quantitative, and we want to understand really the dynamics. What exactly of these gluons is really creating this surface, and why is it a surface in 1 higher dimension? Where are the degrees of freedom corresponding to stuff that moves in this dimension that was not there to start with, and so on. Another general question we can ask is, what are the singularities of scattering amplitudes? Again, at weak coupling, we know that we have, for example, singularities when a subset of momenta become on-shell. This is the factorization. But at strong coupling, we know we have other kinds of singularities, like flat space limit singularities that Juan will tell you about. And what about finite coupling? How do one singularities get softened, another get enhanced? Are there singularities that we might generically expect? What are the general discontinuities of these objects? How should I think of these objects as functions, as analytic functions? What is their properties? And of course, it's not just a mathematical question, because whenever we have some kind of singular behavior, there is some physics associated to it, be it factorization, collinear limits. Basically, a function, the interesting part of the function is not the boring monotonic part. It's typically when you have some corner where something interesting is happening. So by saying what are the singularities, I'm saying what is the physics that is hidden in these objects. More generally, we can also ask, how do scattering amplitudes sit inside a solution of quantum field theory? So we have a scattering amplitudes, and we can have other quantities. We can have a quantity here, another quantity, and there can be relations between all these quantities. For example, we have n equals 4. It's a conformal field theory. We want to ask about the spectrum of operators, about the 3-point functions, about Wilson loops, and about scattering amplitudes. And then all these should start talking to each other. But how exactly? How exactly do they start talking to each other, and then amongst themselves? In other words, how does a quantum field theory look like? Right? So suppose you have a mathematician friend, and You are at night, you had a few drinks, and you feel very motivated, and you tell him, let's show that finite coupling quantum field theories make sense, that they can be defined, and that it's all good, and all these things that people say about path integrals is wrong, quantum field theories exist, and so on. You are all very excited. The mathematician is good. He says, yeah, sure, let's do it. And then the next morning he comes to you and say, okay, let's start what we said. And you say, sure. And he says, okay, can you just show me one example so that I can have some intuition, and then we start trying to prove the general case? And you say, oh, there's a small caveat. I have no example. And of course, then it's hard. So it will be nice to have one, such that then we can try to understand basically what exactly is a quantum field theory. And in that sense, the basic idea, what we believe, is that planar n equals 4 super Young-Mills is sort of the Ising model of gauge theories. At least that's the hope, or in particular planar n equals 4 super Young-Mills. The hope is that it will play an important role in our understanding of gauge theories as the solution of the Ising model played in our understanding of 2D statistical models. I think this is reasonable. Okay. I hope you are motivated. So, any question concerning this general motivation? I had a few more things to say, but I think this is enough. Yes?
You said that those shaded fluid diagrams are leading logs. It's known how to compute subleading logs in RT. You mean the finite terms?
Yeah, suppose, for example, often people have this Reggie theory, for example, for studying high energy scattering, right? The stuff that BFKL and Diglev and all these things. And it's often, I mean, for example, the Reggie behavior of scattering amplitudes, it is not known how to systematically expand around the Reggie behavior. If I tell you, I want a general scattering amplitude where the momenta are generic, and I want to expand it around the configuration where they are very energetic, and I want to systematically expand it. Typically, we like having some point around which we expand. And we know how to do the leading term, very, very high energies. This is well understood, but we don't know how to systematically correct. So what I will try to tell you is that right now we have the tools to answer most of these questions, or to start exploring most of these questions by means of the solution of scattering amplitudes in n equals 4. But the way we will solve it is indeed, as I will tell you at the very end of the lecture, by relating it to one of those other quantities, okay, which is the so-called Wilson loop. So Wilson loops are also standard objects in gauge theory, a little bit less standard than scattering amplitudes. So who does not know what a Wilson loop is? No, I cannot believe that everyone knows. I know you are all very bright, but this is impossible. This would be amazing. This would be way too good. Sorry? Okay, very good. So I'm defining a Wilson loop, W. It's a function of a loop. Okay, let's say a loop. There is a contour C, which is some loop in space-time. Okay, and a Wilson loop, let me define it as the trace of the path order exponential of the integral of my gauge field along this contour x of t dt. Okay. So this is an object. It's a non-local object. Okay, as João said in response to one of the questions, it's a trace of an operator. So if you consider correlation functions of many Wilson loops, they factorize. And this is its definition. And in the remaining part of the lecture, and perhaps a little bit of tomorrow's lecture, I will remind you why these objects are central objects in gauge theories, why these are very important observables. But if really everyone knows, I'm a bit afraid that this might be too basic, in which case, at the end of the lecture, just tell me, and tomorrow I will speed up. Okay, very good. So let me make a few observations. Of course, a mathematician would not write this. A mathematician would write there is an integral of some contour A of A, just a connection. I mean, everything else is just redundant. It's implicit. Indeed, for example, this part here is just dx mu. Okay, and why am I mentioning this? Because this is indeed a notation that emphasizes an important property of these Wilson loops. They are functions of the contour. They don't care of the particular parameterization x of t that you use. If you choose a particular x of t, that means you put your tick marks in a given way and someone else puts the tick marks in a different way. The result is, of course, the same. And you see very well that if you change t to f of t, of course, this is parameterization invariant. Okay? The second comment that what I want to remind you now, so this is here, I'm thinking of this as an n by n matrix, as João and Freddy were using. And this P stands for path ordered. Okay? And if we are doing QED, there is no trace, no P, and it is just the usual run-on Bob phase for a particle going around some contour. Okay? It's just a standard thing. So let me remind you a little bit. Let me define this object. Let me give you the formal definition of this object, then the rigorous definition with this path order. And it's convenient to do it introducing first a Wilson line. So a Wilson line is like an open object instead of a closed loop. Okay? Which is defined as just the path order exponential of the integral of the same thing. So I. Okay? But it goes from a given point x, which can be x of 0, to y, which can be x of capital T, say. Okay? And of course, this Wilson loop W is nothing but the trace of this Wilson line if I take the final and initial point to be the same. Okay? It's not obvious yet why it does not depend on the starting point and so on. This will become clear today or maybe tomorrow. But this doesn't solve the problem of defining it because I didn't define what this object is. So let me just remind you what are these Wilson lines. So let me give you instead of 1, 3 definitions. Okay? And then, of course, I will leave it as an exercise to show that they are all equivalent, but I just want to make sure that people understand. So one definition is to say that this Wilson line, I want to study a given contour, and what I do is I break it into many small pieces. This is, after all, what the definition of this path order exponential is. So this is just, yeah, I should write below, right? Yeah. Okay. This is clear, right? It's just I drew a line and many tick marks. So this is defined as the limit when these tick marks become very, very dense. So this delta t goes to 0. And then I just discretize and I write e to the I a mu at my x of 0 times x dot mu of 0 delta t. And I draw times, because remember, this is a matrix. Okay, so I compute this small matrix. This is very close to the identity. This is 1 plus delta t times this, plus delta t squared times this square, and so on. I multiply this times another one, where now I write the same thing, but I replace the point 0 to the point delta t, and then, etc., until the very last one, e to the I a mu of x of capital T, x dot mu of capital T delta t. Okay? So I just discretize and put many of such factors. How many of them? Well, capital T divided by delta t of them. And then I take the limit when delta t goes to 0. Okay? So this is just the usual definition of path order. Okay? A second definition that I would like to present is just that U, I can define it as an expansion as 1 plus, and I will just compute it as a sum of many integrals. So I write plus the integral dt1 from 0 to capital T of small a of t1. So let me define small a of t. I will define it in a minute. Plus integral from 0 to t2 dt1 integral from 0 to t dt2 a of t1 a of t2 plus integral, let me write maybe just one more, dt1 from 0 to t2 integral dt2 from 0 to t3 integral dt3 from 0 to capital T, and then 3a's at point 1, 2, and 3, plus dot, dot, dot. You see the pattern, where this a, let me write here, a of t is just the exponent. So it's I, a mu of x of t, x dot mu of t. Okay? Okay? And you write these nested integrals. You see, you integrate with the times being ordered, and you compute all these terms. This A is a matrix. The first term I identity is also an n by n matrix, and you just compute this full sum. And let me give you one more definition, which is that this can be defined as saying that the derivative with respect to capital T of my Wilson loop minus is equal to the Wilson loop times the matrix A of t. Okay? With the boundary condition that I solve this differential equation with the boundary condition that if I consider an infinitesimal Wilson loop, I do nothing. Okay? So let me just note, so the first note, let's see what happens in QED. Okay? QED, a mu is just a number. There is no matrix, a 1 by 1 matrix. Then let's see what happens here. Well, then if this is just a number and u is just a number, I know how to solve this differential equation, right? Then from this differential equation, I just know that u is just the exponential of the integral of a of t. Right? This is what follows from solving this just differential equation. When they are numbers, I just exponentiate. It's also obvious then in that case, if they are numbers, all this product of matrices, these are just numbers, it's just exponential of a sum of many terms, and this is just the integral. So of course I get the same thing there as well. And here, if they are numbers now, this order doesn't matter, and I can replace this integral, which is ordered by 1/2 times the full integral, this by 1/3 factorial times the full integral, and this becomes again just the expansion of the integral upstairs brought down as an expansion of the exponential. Okay? So all definitions you see for QED lead immediately to this expression, but I leave it as an exercise, which is a very simple one, to show that 1 is equivalent to 2, which is equivalent to 3. Okay? Of course, you only need to prove 2 of these arrows, but actually it's, for any pair, it's easy to find a simple derivation that leads to any of them. Do you want me to do one of them? If so, choose one and I can do. Otherwise, it's a simple exercise. So now we know what this object is, and let me then remind you where it shows up, a few places where it shows up. It's really ubiquitous, it shows up everywhere. But let me give you an example of a few of those places where this object appears. So, as a first example, let's consider a propagation of a particle from a point x to a point y. Okay? And let's do first a chargeless particle, then we'll do an electron, and then we'll do a quark. Okay? Let's increase in complexity step by step, because once we do the chargeless particle, adding the gauge field will be rather straightforward. So what is this? What do I mean by this? This I mean that I start at position x, I evolve, and then I go to position y. Okay? And how are we going to compute this? We are going to say that this is just the integral dt from 0 to infinity e to the minus t times capital P squared plus m squared. Okay? I'm just reminding you a couple of basic things about first quantization. And then this looks like an Hamiltonian exponential propagation for a given time t. And what we are going to do is insert several times the identity. And break down this exponential into many small pieces, such that the fundamental building block that we have to compute is xi e to the delta t times p squared plus m squared times xi plus 1. Okay? So, of course, the gaps you can fill in, right? I'm just putting the identity in many places, and we have to compute this. And here it's convenient to introduce further some complete base of momenta, and that's because pi acting on p just gives the number pi, and then I can take out the exponential. So when we do it, this full thing becomes then, let's see, from this pi acting here, we get e to the I pi times xi. From this pi acting there, we get minus xi plus 1. And from the pi acting this exponential, that's right here, we get e to the minus delta t times pi squared plus m squared. Okay, can you read? E to the minus delta t pi squared plus m squared, I, pi, and so on. Xi minus xi plus 1. Then we have many of such terms, and pi we can integrate because it's quadratic. Okay, so we complete the square, so you see what you get. When you complete the square, you get xi minus xi plus 1 square. So all in all, when we are done, we conclude that the propagation from a point x to a point y is equal to the integral over all possible paths that go from x of 0 equal x to x at any given time t equal y of exponential of the integral. And then there is some x dot square, which comes from completing that square and taking the continuum limit, plus m square dt. Okay? Now, as a further step, to make it a little bit better, let me point out that what we did here, we could have chosen, let me do differently. What we did here is we took the time from 0 to capital T, and we divided it in equal spaces. But we could, of course, have chosen a finer grid here, and a bigger grid here, and finer, and so on. Right? So we could have chosen, and we should get the same result, of course. So how do we find a way of, in this formulation, allowing for any possible way, any possible such grid? That is, to have any different metric between 0 and t. Well, if we had introduced the density of tick marks, it would show up here as some over some function e of t times some density e of t, where this e of t has the transformation properties that you need for this to be parameterization invariant. So when you change t to f of t, the measure gets an f prime, and this e gets 1 over f prime. And of course, because this metric doesn't matter, we can integrate over it. And because it has no kinetic term, we can even eliminate it by its equations of motion, which tell you that you can fix E to be equal, if you just compute the equations of motion, to square root of x dot square over m square, which leads to the famous result that to study the propagation of a particle from one path to the other, we sum over all possible paths of the particle e to the minus mass times the length, where this length is just the integral of square root of x dot square dt, which is manifestly parameterization invariant. Okay? So this is the result that you know. I just wanted to remind you of sketching the kind of main steps, not very rigorous, but okay. Just so that you get a feeling, remind you a little bit of how it comes about. Right? So this is the famous thing. A particle follows geodesics. So if the mass is very large, the particle wants to minimize the length. So, and this is a geodesic. Okay? Now, what if we had a gauge field? Well, if we have a gauge field, then all we do is we change P to P plus IA, and we follow the same thing. So what would happen is that here, this P here would be changed, would be shifted, this one here. And therefore, when we complete the squares, we have to add an extra term with a mu times the difference of x's. So what would happen with the gauge field is that we would add here plus some extra term, where this extra term is just I a mu of x of t x dot mu dt. Exactly the term that we wrote before. Exactly the term that we wrote before. Okay? And you see that the way this is defined, because we break it down into pieces, what would happen if instead of being just a gauge field, if it was a matrix valued gauge field? Well, exactly the same thing, but we will not end up with exponential of an integral, but following the derivation of this path integral, we will end up with a product of exponentials, 1 per each slice, which is our definition number 1 for the path order exponential. Right? So what we conclude is that when we have a quark propagating from a point x to a point y, this is given by a sum over paths, exponential of minus mass times the length, times the associated Wilson line that goes along the corresponding path. Okay? So this is one example where we see that Wilson loops appear in a rather straightforward way as we study propagations of particles in the presence of the gauge field. So for example, if we have a solenoid and we go up an electron through the right or through the left, what's the difference in phase? Well, it's the integral through the left minus the integral through the right, which is the total integral of the gauge field, which measures the flux tube pierced by this solenoid, which is just the usual Aharonov effect. How is it? Aharonov. Very good. Effect. The gauge field. Very. Great. Is it clear? Any question here? So, okay, very good. Now, let's do some computation to see that the results that come from really computing expectation value of these Wilson loops are very reasonable and which they allow us to recover things that we know very well. Okay? So let's now start thinking about really computing these Wilson loops. And suppose we want to compute this Wilson loop at one loop. Here there's no black hole, right? At one loop. So at one loop, what do we have? We take our Wilson loop. We take our favorite definition. I don't know which one, but for example, the one where we expand in integrals. And we compute the average of these objects. Now, the average, the 1-point function of the gauge field is 0. There's no 1-point function. What about the 2-point function of two gauge fields? Well, that's not 0 anymore. The two gauge fields, they have a propagator between them, and I just evaluate them by the propagator. So at one loop, what is called one loop is that second term, which is exactly that we draw like this. We say that we have some a of t at some point t, and it communicates, it propagates with some other point. So let's write this explicitly, and then there are other terms. Okay? Other terms at higher loops. Okay, one loop and higher. This is the one loop diagram, is this one. So what is this diagram? It's just the integral dt1, dt2, and then we have the propagator in position space is just x of t1 minus x of t2 square. Okay, then there is delta mu nu, and this is will lead to a scalar product x dot of t1, x dot nu of t2. Okay, it's just the expectation value of the two gauge fields. And this is just x, we sometimes write like this, x dot 1 dot x dot 2 divided by x1 minus x2 square. Okay? So this is what you have to do. You take 2 points and you compute this quantity integrating the gluons along the loop. Okay? This is what it gives to leading order. What about higher orders? What about these dot dot dots? Now it's very important to distinguish. One thing is QED, one thing is Young-Mills. Okay? Now QED is very simple because QED, this line is a photon, right? Photons don't interact with each other. So what happens at higher loops in QCD? For example, when I have 4 gauge fields, the 4 gauge fields you just connect them as if they were not there. So this just gives the square of the previous result. Okay, and the result basically in QED exponentiates, and this becomes equal in QED to just the exponential of this fundamental integral of a gluon going from one point to the other. That's the full result, the exact result in QED. Okay? Whereas in Young-Mills, we also have more complicated stuff where we have a Wilson loop, and for example, the gluons can form a cubic vertex in the middle, and so on, and it is just a very much more complicated quantity. It's important that it's much more complicated because you see that these diagrams full of vertices in the middle and so on, those are the ones that will look like a surface, right? When we have all these vertices in the middle, all these gluons, and you draw all this in the plane, and after drawing 1 million loops, you cannot distinguish it from a smooth surface. And this is the surface that will be the surface in the DSCFT that appear in large n limits of nanobillion gauge theories. Okay? In QED, however, it just exponentiates neatly. So let's just focus on QED for now, or if you want, on Young-Mills at one loop. At one loop, you cannot distinguish both. And let's And let's consider the example of a Wilson loop for a particularly simple contour, a rectangle. Okay? So let's consider a rectangle where this distance, r, is much smaller than this distance, beta. Okay? Okay? So let's consider this Wilson loop and see what we get. Okay? So what is the intuition for this Wilson loop? If we think that this represents a particle going along this trajectory, what kind of particle is this? What kind of particle is this? So we have a particle. So let's say this is time, this is Euclidean time, this is space. And we have a static particle that is always here at any time, ta 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 ta. And we can think that here we have another particle that is also static, separated by a distance r. And then we are connecting at the very top and very bottom, but this is a bit irrelevant. It's just to make a loop. What's important is that we have these two lines, static lines, for a very, very long time. So this is equivalent, of course, to adding to the Lagrangian. Lagrangian goes to Lagrangian plus integral to coupling some matter to your gauge, to your theory, where this J, what is this source, is just two static particles at x equals 0 and x equal r, right? Such that this J mu is just, for example, delta of x equals 0, delta mu 0, plus another term at x equal r. Okay, just put two sources there, static at position x and 0. Okay? And this, of course, then if you compute this path integral with these extra sources, what do you expect to get? And we will see that it works perfectly, of course. We expect this to be e to the minus beta, beta being time, this time, big time, times the ground state energy. That's what the path integral gives. But now it's the path integral in the presence of these two heavy particles. And we divide by the partition function. So the vacuum energy just cancels out. And what we are left is the potential bit that gives the interaction between the two particles, V of r. Okay? So say in Young-Mills, we expect this potential to grow linearly, and this will be a sign of confinement. Whereas in QED, this potential should decay like 1 over r and should be just Coulomb law. Okay? So, again, this is when beta is very large. So let's see what we get. Let's see that we indeed reproduce, of course, what we expect. This wet one, does it work much better than the other one? I remember when I was seeing, I preferred it, but this is much tougher. For me, this is like a sport. should not do sport for the rest of the year. Okay. Very good. Okay. So now let's do this. Let's do this simple computation. So let's take a rectangle. And let's consider the various diagrams that can show up. Okay? Why do I say various? Of course, it's all the same. It's a gluon or a photon going from one point to the other. But now there are different possibilities. For example, the first one we could consider, let's consider the one that is obviously the interesting one, which is when the photon goes from one edge to the other. Right? These are the diagrams that know about the separation and that are therefore the most interesting ones. Right? That know about this distance r. So what do we give? Let's compute this. So we get an integral. Let's suppose we say we use dx dy, where x is this point goes from 0 to beta, and y goes from 0 to beta as well. So we are choosing this parameterization, where we parameterize with the same distance. Then here we have x minus y square plus r square, right? Just the distance between the 2 points, right? This distance is this. Just Pythagoras theorem, right? So it's this separation and this separation square, this distance square, right? And upstairs, what do we have? The scalar product, but this is just 1, right? Because we are choosing this parameterization, x and y being equal to the length. So x dot dot x dot, they are pointing in the same direction. It is just 1, right? And now what do we get? We get, of course, that this is just integral. So I can rescale x and y by r. Did I do everything right? Sorry? I did something wrong. What did I do wrong? 1 second. No, it's okay. It's okay. So this is translation invariance. So all that matters is this separation here, delta x. The center of mass just gives an overall beta. Of course, we are thinking beta is large. So we have beta as the overall center of mass times the integral of this over this delta x squared plus r squared, where now this can go from, say, minus infinity to infinity. It doesn't matter now, it converges. And then when I compute this integral, if I now rescale delta x by r, I get beta over r times a number, but we did not keep track of pi's anyway, so it doesn't matter. Okay? So this is good. So you see that indeed this leads to a contribution to the potential V of r equals some number over r plus whatever comes from the other diagrams. But even before computing the other diagrams, we are already happy. We already got Coulomb law, right? Just the potential, 1 over r potential between my particles at leading order. Okay, so now let's continue and get some intuition about the other terms. Okay. Oh my God. Let me do like Rafael was doing. Rafael was coming here and erasing right away a few blackboards, right? Very good. So now what about other diagrams? So what about the case where one gluon is in the top edge and the other gluon or photon is in one of the side edges? Can someone tell me what those would give? Did you understand? So one photon is in the top and one is on the side edge. Anyone? Sorry? 0. Why? Sorry? Sorry? Exactly, because they are orthogonal. So this x1 dot dot x2 dot, they just give 0. Okay? Because the velocities are orthogonal. It's couples to the velocity, to the scalar product of the two velocities. So these diagrams here, in this case, they are just 0. We are left with one more class of diagrams, which is the diagrams where the two are on the same edge. So what would these guys give? This would give the same thing, dx, dy, but now just x minus y square. Now there's no separation r square. And now what happens? What happens is that now we have a problem. Now we have a divergence. So again, this gives something. This divergence can happen at any point in the loop. Here, 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 here. At any point in the loop. So there is the total length of the loop. This length, if you want to be precise, is twice beta plus twice r. If beta is very large, we just care about the twice beta. Times this integral d of delta x over delta x squared, that if you regulate by saying that the two photons cannot be too close, this would lead to 1 over a cutoff divergence. So epsilon is now a small cutoff. Right? So all in all, we see that our V of r, okay, which is defined, again, let me be here, is defined as the limit when beta goes to infinity of minus log of the Wilson loop 1 over beta times log of the Wilson loop, is what? Is the Coulomb law, right? Plus some constant shift, some shift over epsilon, where epsilon is a divergence. Okay? Now, let me make two comments. The first comment is that, of course, if we are interested in the force between quarks, which is a derivative with respect to the separation, I don't care about this constant shift. Right? This is good. So it doesn't affect, it is just like an overall shift. But in fact, it can also be given a more physical interpretation. If you remember, perhaps we still have it here. No, we don't. It was right here. If you remember that the propagation of the particle, what does it give? It gives exponential of the mass of the particle times the length of the Wilson loop times the Wilson loop. So this is giving a term that is also the length of the Wilson loop times the divergence. So I can think of this term as a mass renormalization. I can think that I have some bare mass, and this mass is getting corrected, and I don't measure the bare mass. So all I measure is the mass that couples to the length. So what I measure is whatever I was calling before m, let's call it m0 to remind ourselves that this was the bare mass, plus this correction over epsilon, and now the full thing let me call m, and this is the physical mass. Okay? So I can think of this effect as renormalizing the mass of my probe. Okay. So this was the Coulomb potential in QED. What about in n equals 4, say? In n equals 4 is a conformal theory. And because it's conformal, because it's a CFT, so there are no scales, and therefore the potential V of r, just by dimensional analysis, must be a function of the 't coupling lambda divided by r. Okay? So it must be also Coulomb potential. And the challenge then is to compute this lambda. This lambda starts like in QED, 1 over 2 pi lambda at very small coupling. If we have kept track of all the pi's, this is what we would get. And then it goes to some other value at strong coupling, okay? When lambda is very large. And this was indeed, Juan Maldacena did this computation in 98, like 1 year after ADS-CFT, was one of the simple observables that we could study using ADS-CFT, because it has a very simple geometrical description, these Wilson loops. how do we study this Wilson loop, that strong coupling using ADS-CFT? We draw the boundary of ADS here in point-correct coordinates. That Juan will explain in excruciating detail tomorrow. So we'll tell you all about it, but I'm sure you saw these pictures. You have a boundary of ADS. And you consider your contour. In this case, the contour is a very long rectangle, but it can be any possible contour. And then you draw a minimal surface that ends on this contour, and you compute its area. Okay? And the claim is that the Wilson loop is given by e to the minus square root lambda over 2 pi times the area of this minimal surface. And this minimal surface, however, because you approach the boundary, and you remember from Juan's lecture that the metric is this, and Juan will also tell you more tomorrow, but as you see, as you are approaching the boundary, the metric is becoming very, very large, so it costs lots of area to go all the way to the boundary. And indeed, this area is infinite, strictly speaking. So what do you have to do? You have to go here and cut at the small epsilon away. And you cut here also at a small epsilon on the other side. And then this area contains two terms, contains a length over epsilon divergence plus some regularized part that is more interesting and depends on the radius, r. And again, this is not surprising. The meaning is the same. This is just the usual mass renormalization of my Wilson loop now at strong coupling. And this interesting part is what will give me this alpha of lambda at strong coupling. Okay? And just for completeness, let me just show you that it gives a non-trivial prediction. It gives a prediction for pi square gamma to the 1/4 to the 4th power times square root of lambda. Okay? So the idea is that at finite coupling, we have lambda, we have our alpha of lambda, and we have some function that starts linearly and goes to square root, and then it interpolates somewhere in between. And just 1 or 2 years ago, Maldacena, Severe, and Correa proposed a set of integral equations describing all this intermediate region. But it's still an open problem to just put those equations in a computer and do this plot. So if someone is interesting, I think it will be very interesting. But it is not like it is just put in a computer and do it. There is something to understand exactly how to do it, because those equations, naively, strictly speaking, they look like some sums don't converge and so on. But I think it's an interesting project to just complete this curve. And in principle, this can be done by following this work that I said of Correa, Severe, and Maldacena.
Question?
Yeah?
Sorry if you said this before. Sometimes Wilson loops in n=4 also involve exponentials of scalars. Besides
Exactly,
the exponential of the gauge field. Is that what
Absolutely.
this is?
Yeah, in n=4, this is what I have in mind. Yeah, I'm just glossing over it. Yeah. And I'm glossing over it for a good reason, that the Wilson loops that we will be studying in the lectures will be the usual ones. So I don't want to go into those details of the scalars. Yeah, but that's true that it's possible to define a supersymmetric version of these Wilson loops, where in the exponents it's not just the gauge field, but also the scalars of n=4. Yeah. No, that's a very good question. No, this one here, there is no hope of summing gluons and ever getting to this result. It's very, very tough. Or there is little hope. And this one here, it's very hard from the point of view of string theory. This describes strings with very, very low string tension. They are vibrating like crazy. They go to this boundary, but instead of giving a minimal surface, these surfaces fluctuate as crazy, as wildly as they could. No, this comes with a different number. For example, this number is square root lambda over 2 pi here, whereas there, whatever it will be proportional to lambda again. So it will be again. No, the epsilons can be the same. They can have exact, but what multiplies them, the precise number that tells you how the mass is corrected, is different. Okay? In any case, as I emphasized, this is not the physical part. The physical part is really the part that depends on the shape. This part that is the divergence, we know how to subtract it well. For example, you can consider a ratio of two curves take your favorite Wilson loop, Mickey Mouse shape, and divide by a circular Wilson loop where the perimeter is the perimeter of the Mickey Mouse. Okay, that just cancels, and we can use a circle as a reference Wilson loop and just divide everyone by circles of given lengths. Okay, very good. So, and as I said, this is in QED and in n equals 4, which is a CFT. If the theory were confining, like in Yang-Mills, the potential would grow linearly with a string tension, and it would be much more similar to the flux tubes that Raphael was describing. The flux tubes that Raphael was describing were exactly these flux tubes, which had this ground state energy. Remember that he was showing that was linear, and then he was subtracting the linear part so that he could see the structure of the excitations on the flux tube. You could also, this is exactly the linear behavior that you would get in Yang-Mills by studying these Wilson loops. Okay, very good. Now let's go back a little bit to the definition and to the math of these Wilson loops, just so that I mention a couple of points that are important and that constitute further motivation for studying these Wilson loops. In particular, I want to tell you that these Wilson loops that we have here, that they are gauge invariants, and that they are related in a very direct way to more standard things like local operators of the theory. So they are these fancy non-local probes that, as we see, they are nice probes of confinement and so on, but they also have very direct connections to more standard things like local operators and so on. Okay, so this is what I want to tell now. So the first thing I want to point out is that once we have, perhaps I should, sorry. Suppose I have my Wilson loop, and I add here a small bump, minus, okay, now good luck drawing the same contour. More or less. Okay, so this was where the bump was inserted. What is this equal to? Okay, so we insert here a small bump. Okay. Perhaps I will just say the result, and I will leave it as an exercise to show it. So, yeah, I think I will just skip all the algebra. There's nothing very fancy about it. Okay, we get the following. We get, so there is some dot, dot, dot here. This part is not important. So we get the same Wilson line. And here we will insert something, and I will tell you what we will insert. And what we insert here is just, so let's say this direction is the direction x, and this is the direction y. So I'm putting a square in this plane. I will get dx ay minus dy ax plus the commutator of ax with ay. Okay? So what we get here is nothing but what we call the field strength, or the component xy of the field strength, because we are putting this in the plane. So what we see is that what we get when we consider a Wilson loop with a small deformation is an insertion where we have some Wilson line propagating up to this point. Then we insert the field strength at the point where we deform, and then we continue with the Wilson line a little bit more. Okay? So, I mean, the simplest way of proving it is, for example, using this definition with a small exponentials of a, e to the delta t times a. You put here an exponential, an exponential, an exponential, minus the exponential like this. So you see easily that, for example, these derivatives will just come from exactly this difference, this point minus this point, and so on. Is it okay? Do you allow me not to do it in detail? You get this times epsilon square, where epsilon is the area of this square. So if this is epsilon, and this is epsilon. Okay, you can do it more covariantly. If you have some area element, you get the area element dotted with the field strength. Okay? So why do these things all work out nicely? Okay? So in particular, we see what I want to point out is that, so what we conclude is that a small bump is equivalent to an insertion of an excitation. In this case, an F, but it could be something else. So why are all these things working out correctly? So under a gauge transformation, A goes to omega, A omega minus 1 minus omega d omega minus 1, whereas gauge invariant operators, gauge covariant operators go transform like this, and also other fields. If you have a joint scalars, they transform like the field strength and so on. Okay? And because of this definition, of the first definition, our gauge field, our Wilson line, under a gauge transformation, is not invariant, but it transforms under omega of the initial point times u times omega minus 1 at the final point. Okay? So what happens when we have the Wilson loop with an insertion, and you try to understand whether things are gauge invariant or not? When we have our Wilson loop with an insertion of an F and so on, how does this transform? Well, there is the first part of the Wilson loop times omega of the point where we insert times, and then F transforms with omega minus 1, and then there is the remaining part of the Wilson loop with omega, and they just cancel out, leaving a gauge invariant result behind, assuming that the endpoints are closed or treated in the same way. Okay? More generally, Wilson loops are the only way we have of defining non-local operators. Suppose I have a quark q bar. A quark q bar transforms under q bar omega minus 1, and the quark q in the fundamental that transforms into omega q. Then suppose I want to describe a quark at a position x and an anti-quark at a position y. Now this is not gauge invariant. This doesn't make sense. I cannot just say, let me take the operator q of x times q bar of y. This is just nonsense. It's not gauge invariant. I do a gauge transformation and it transforms. How do I make it gauge invariant? Well, I take these operators and I unite them by a Wilson line. This is good, right? Because now my operator q bar u q, if I do a gauge transformation, I just insert here omega minus 1 omega, and here omega minus 1 omega, which is the identity, of course. Okay? Very good. And then how do we think about this Wilson line that is here? How do we think of something stretching between a quark and an anti-quark? What stretches between a quark and an anti-quark? Which was in the title of Raphael's lectures. A flux tube. This is a way of thinking of the flux tube, or a string, if you want, between the quark and anti-quark. And this idea that Wilson loops are very much related to the flux tube is indeed not just some cartoon. It's the way in practice people in the lattice study these flux tubes. So let me just remind you of something that Raphael also told you. About how do we study these excitations of this Wilson loop in the lattice. we take a flux tube in the vacuum and we add some excitations, he was saying. And now I will connect these two last blackboards that we wrote. So you remember what was the statement? The statement was that we take, say, a cylinder. Okay? This can be identified. And then, not to deal with the endpoints, with the quark and antiquark, a clever way is to just wrap the Wilson loop around the cylinder. So we just consider a Wilson loop that just wraps around this cylinder. So this will describe the vacuum of the Wilson loop. And then what do people do in the lattice? Instead of putting this just straight Wilson loop, they add a small bump here. Okay? And they do it at a given position, and they consider an average to give it some given momentum. Okay? And then they consider two-point function of two such objects. And from this, they get a sum over the states. If this separation is tau, e to the minus tau times the energy of the excited flux tubes with some coefficients. And what are these energies? These energies are just the energies. I imagine my flux tube between, and there can be some bumps, some phonons moving with some momentum p, and they have some energy of p. And this, for example, is how we would access them, where these p's are quantized to be 2 pi n over r, where r is the length of this circle. Right? You see? So this is this idea. And if you want, you can consider linear combinations that give them particular angular momentum and so on to isolate particular quantum numbers. Yes?
Does something fix the particular path that you're supposed to take between you guys? Not some ridiculous
Yeah, you can. You can. Yeah, so yes, indeed, there's no particular choice here. And the flux tube is what is flowing here, right? What we are putting here is we are putting an operator that disturbs the vacuum and that will have overlap with the dynamical flux tube. This is not dynamical. You choose the path, as you were pointing out. Now, if you choose a path that is just straight, and then if you cut, you put a plane, like David was saying, we cut by planes and see what's flowing. What will be flowing here? What's the moment of the excitations? Well, if we don't put any defect, they cannot have any momentum going here. So, well, yes, there could be a flux tube wrapping this around this circle, but it will be the vacuum. It's fine. It's still interesting. It will give this linear growth with the size of this cylinder. But what if I want to consider some perturbation here that will have overlap with excitations that are moving around here, these excitations of the flux tube? Well, then I need to put some disturbance on my Wilson loop. Okay? So you are right that this, I should think more like some boundary condition for my flux tube that then evolves dynamically. Okay? Very good. So, for example, along those lines, what's the simplest possible Wilson loop I could consider? It's a Q bar, a straight line, and a Q. Right? This is just the simplest possible Wilson line. So let's just remind you, what is this? This is nothing but Q bar, this Wilson line times Q. But this is also just Q bar of X. And then, if you would like to translate, you say I put my Q of X, and I translate by some separation A, if this is the vector A. But how do I translate? I dot it with the derivative, right? I make exponential of A times the derivative to translate. But what derivative? Not usual derivative, but rather covariant derivative. Okay? This is how we propagate things. Okay? So this is things you can easily check. They are the same. And this language is kind of useful because you see that this now looks like a local operator. If I expand this, I get 1 plus A times derivative plus A squared times derivative square plus A cubed times derivative cube. It looks like a linear combination of many local operators. So this, for example, starts giving some relation between Wilson loops and local operators. And in fact, this is the second example. The first example we saw was already here. By iterating this further, I could imagine expanding the Wilson loop around a particular point, which will be a bunch of field strengths and a complicated linear combination of field strengths. Okay? So there are these relations between Wilson loops and local operators, and in particular, you can easily imagine that what are the operators that matter? The ones with few derivatives or many derivatives? If you want to stretch two operators, do you want to do it with 3 derivatives, for example? No, right? 3 derivatives, you go epsilon. You don't stretch from here to there. You need many, many derivatives. So the precise connection is that there are a connection between Wilson loops and local operators of high spin. Right? Number of derivatives like spin. So large spin operators, local operators with many, many covariant derivatives. And in that language of operators with large spin, for example, a Wilson line with an excitation would correspond in that language to having Q bar, then many covariant derivatives, and then say some field strength, and then many, many covariant derivatives, and then the quark. And giving it some momentum here, by putting it at some position and making linear combination would be the same thing. You put some derivative, some f here, with some n derivatives to the left, s minus n to the right, and you also give it a linear combination. Okay? And this would be the counterpart of that, when the number of derivatives are very large. Okay? Okay. So, suppose then we want to start studying. Now we know what these Wilson loops are, we know its math, we know its motivation, and let's say that we now want to compute these Wilson loops. By the way, there are claims that these Wilson loops, because you can indeed expand them, you can consider, say, Wilson loop for a very small square. You just expand, and this is something like f squared plus dot dot dot. Then you do a slightly different shape, and you capture other powers of f, and so on. And there is this idea or this hope that if you would study Wilson loops, you would know everything about all possible local operators, that these contain all the information about the gauge theory. So this would be as good as studying, say, correlators. Of course, in practice, it sounds a bit like wishful thinking, but at least it's common law. So anyway, suppose we want to study Wilson loops in n equals 4 super Young-Mills, or in a generic conformal gauge theory at any value of the coupling. Now, what would be the first obstacle that we find? Well, there are many obstacles. Of course, computing anything at finite coupling is a challenge, because we cannot do perturbation theory or holography. We need to do something more powerful, which, as we will see, will come in this case in the form of integrability, but this we will only get to in the 3rd lecture. But an obvious obstacle that we would immediately face is that these objects are very complicated. In particular, because they are functionals of contours. It's not something... it's a complicated object. They are functionals of a given contour, right? And contours are kind of complicated, right? So, I don't know. If you have in a conformal field theory, suppose I have a snake and I apply a conformal transformation, I don't know, it can become a dog. Huh? Who knows? It's so hard to have an intuition about conformal transformation. I just start with something, do a conformal transformation, becomes something completely different. So if I want to have an object that is invariant under conformal transformation, something that, if I want a nice subset of Wilson loops that I can describe in a conformal field theory, it's useful to remind ourselves that there is something that we do have much better control over, which is straight null lines. Under a conformal transformation, they go to a straight null line. Huh? Okay, it's a basic fact. So this motivates studying not this zoo of animals that under a conformal transformation can change all these animals amongst each other, and therefore it's quite complicated. But let's study Wilson loops whose contour is a sequence of null lines. So it's piecewise null lines. So this is what's called a null polygon. Okay? This is kind of nice because under a conformal transformation, the null polygon goes to another null polygon. It looks a bit different, but it's still a null polygon. Okay? So null polygons are nice because in a CFT, they are parameterized by the cross ratios of their cusps. You see, if you take the cusps, you take, say, 4 cusps, and you make a cross ratio out of these 4 cusps, say, for example, under a conformal transformation, these 4 points go to some other 4 points, but the cross ratios are invariant. So it's a much simpler data. It is just you give me a polygon with n edges, I construct all possible cross ratios, and this object is a function of the cross ratios of a polygon. Much simpler than this function of the shape of a penguin. Right? It's a much easier object to handle. Okay? This is one motivation. So it can be a polygon with any number of edges, and so on. And it's parameterized by a function of these cross ratios. Okay? And not only it is much simpler, but any shape that I want, even a dog, can be approximated by a sequence of many, many null edges. Right? I mean, it's like pixelizing, like how computer games are done, right? You just you break any smooth contour as many, many, many discrete edges. Okay? Now, of course, you can say, okay, but come on, that's wishful thinking. You are never going to describe a smooth contour by a sequence of many, many null edges. But it's actually perhaps not true. For example, at strong coupling, after we had a solution for these amplitudes, John Toledo, for example, he understood exactly how to describe these dogs by taking many, many null edges, and it's right now our best way of computing smooth wheels minimal surfaces in ADS that end on any general curve. So it's perhaps not so much wishful thinking, and perhaps it's something that can indeed be done at finite coupling. So that's problem number 2. So once we will solve this, then we might want to take this limit. Or maybe not, because there is another important reason why these polygons are interesting just by themselves, which is the relation, and finally we will close by connecting it to the beginning of this lecture, which is the relation to another very important observable in this gauge theory, which is scattering amplitudes. What happens is that in this theory, these polygon Wilson loops in this theory, so the second very important motivation is the following. Let me start with a statement. Take a Wilson loop where you have some polygon. This is a null polygon. So let this edge be k1, this one be k2, and so on, where this k square is equal to 0. Right? Like in Freddy's lecture. So we have a bunch of k's that are equal to 0. And let's consider another object that depends on the same data. What is the other object that depends on the same data? Is a color-ordered amplitude. Okay, remember this color order that Freddy was introduced, where particles are ordered in the same way, 1, 2, 3, up to n. This also depends on this set of ordered momenta, all of them null. And they all add up to 0 here, as Freddy explained. And here, because the polygon is closed, the sum of these vectors is also 0. Right? So the data is the same. Now, what is known is that this object has infrared divergences, which are physical, and they are related to scattering of massless particles. And it is known that this object also has divergences. They are UV divergences associated to the cusps of the Wilson loop. Okay? These are new ones. These ones we did not see. Remember that we had a cusp before, but it was 0 because the scalar product was 0. But if it was not 0, you would get a new divergence when these points are approaching each other. Right? So this is a new divergence. It's the only one here, because here the divergence proportional to the length you don't have, because all edges are null. So this is a polygon. The total length of this polygon is 0, because all edges are null. But you do have cusps here, and here you have infrared divergences, which you can associate to this kind of diagrams. And there is a known fact in all gauge theories that the divergent part of these two objects is the same. So I can say that the two objects are the same. If I re-equate them, then there is some finite part that I need to compute if I want to really write a correct equation. Now, it turns out that there's nothing here. So this is just equal to 1 in n equals 4 super Young-Mills. And the relation, you see here, you have some kind of relation that exists in any gauge theory between infrared physics here and UV physics here. And what kind of relation in string theory maps UV and infrared and tends to change things of size r to things of size 1 over r? What? T-duality. And indeed, this relation here was hinted from T-duality of the string dual. I think the story is really beautiful because from string theory, this relation is very natural if you just study minimal surfaces. You just study this minimal surface, and you see that the two minimal surfaces are related by a T-duality. Then you know that this equality is true at strong coupling at least. But just based on this intuition, you conjecture. Perhaps it's true always. And then you ask people that do really honest computation, can you please check if this works at weak coupling? And there was a beautiful computation at 2 loops by a big group of people doing amplitudes of Dixon and collaborators, and by another big group doing Wilson loops of Hahn and friends. And at the time, these objects, you could not even study them analytical because 2 loops was too hard. As I will tell you, we are now reaching the frontier of 5 loops. But just a few years ago, 2 loops was still too hard. And they were just computing numerically, both sides. And making a table of numbers here, a table of numbers here. And then they just send each other, and the numbers were just agreeing each other perfectly. A beautiful example then of understanding. And now it's much more well understood from the point of view of this T-duality, fermionic T-duality, the fact that the two objects have the same integrand. There is a lot of good understanding. Anyway, so as we see, this is an extra very important piece of motivation. If we study these Wilson loops, we kill 2 birds with 1 stone. We get information about scattering amplitudes of the theory as well, besides all the awesome things that I tried to tell you about Wilson loops. So in the remaining part of this, so this concludes the motivation lecture, and now let me just tell you what we will do next, and I will finish here, or maybe I will just say by word since we are running out of time. So next, first thing we are going to do, like in CFT, it was very important, and like Freddy's lecture today, it's very important to understand variables. And now we see that we have to describe null polygons. So it's very important to have the right variables for describing null polygons. So luckily, Freddy is, of course, indirectly introducing these variables because the data is the same. But tomorrow, I want to complement a bit Freddy's discussion by introducing some particularly suitable variables that will highlight the physics of the underlying flux tubes. Okay, so first we'll start with just forgetting now about all we said, and we just ask, let me study geometry of null polygons. How do I describe null polygons in an efficient way? How do I study this geometry? Then we will go and say, okay, now I understand the variables, but I have the problem that this result is true because both sides are 0, because they have all these infrared divergences that make them strictly 0. So of course we don't want a duality because the two sides of the correspondence are 0. We want something more interesting. So as a second step, I will have to tell you how to go from this result that is strictly 0, it's e to the minus infinity. How do we go from this to something regularized? How do we isolate the cusps? And how do we remove the divergences and define something proper? So that will be step 2. When we will have the variables and the regularization, both will hint at the physical picture, and that's where flux tubes and pentagons will show up, which, as you will see, are the natural counterparts of the building blocks in a CFT 2 and 3-point functions. We will identify the analog in this context. This we will do with the help of integrability, is how we will compute these objects. And then in the last lecture, I will tell you about some advanced topics, where in particular we will start addressing some of the questions that we started with. So that's the plan. Thank you. Questions? Very good. So the question is that I lied a little bit. This one here is only specified by case. But as we were seeing very thoroughly in the morning, as Freddy was explaining, this one depends on more data, like the helicities of the particles. So how can this be true? Also, as Freddy was pointing out, this object transforms under the little group. This is a number. This is 1 plus something small. So how can this work? I mean, it looks like I'm lying from the very beginning. But I'm not. So the idea, of course, I am in the sense that, yeah, I'm a little bit. So what is this amplitude? Okay? This amplitude is equal to what Freddy wrote, which is the 3-level amplitude, which contains the delta function of momentum conservation, for example. That is not here. There's no such delta function. That contains all these brackets. You see, all this 1, 2, n1, and so on, that carry a little group that this guy doesn't have. So you write this as this 3-level part. And this 3-level part in particular, as I think Freddy will explain tomorrow, it also contains some fermionic variables that allow you to pick different components so that you can say who has positive helicity, who has negative helicity, and so on. You will probably, right? And dressing this 3-level part, when you consider these amplitudes that are MHV, which are the first non-trivial amplitudes, dressing this 3-level part, there is now something that no longer carries helicity weight, no longer carries nothing, and this is what can be identified with the Wilson loop. And then you ask, what about not MHV but NMHV and so on? Can this be extended? And the answer is yes, and it's very interesting. And perhaps at the last lecture I can tell you more about it. Or you can ask Lucia. She's working on that. More questions? Yeah.
If you want to insert other local operators in the Wilson loop, do they look still like spikes? It looks a bit like you need something which has dimension 2. But that's because you want to integrate it and then have some size.
Yes. So what can we do? So the question is, what can we do if we want to insert other things on the Wilson loop? And for example, suppose we are describing not the flux tube of QCD, but some flux tube of a theory that contains fermionic excitations, for example. And I want to describe here, in the middle, a flux tube with a fermionic excitation. What can I do? Well, I just take the Wilson loop and by hand I insert a fermion there. Or if I have a scalar in n equals 4, for example, I can put the scalar by hand there. So this is one cheap trick. You just put the field instead of putting the bump. Now, a geometric meaning, the only thing we know is that something that is not forbidden by the quantum numbers will appear, like in the OP. So if I consider a bump, I can consider a gluon. But this will also have overlap in the middle to a state that has, say, a gluonic excitation and, for example, a singlet pair of scalars, because this has the same quantum numbers as just one gluon. Of course, it will have a much smaller overlap compared to this state, so it will be hard to dig it from the numerics. So if I would like to dig it from the numerics, it's better if I consider the state by hand that is much closer. Otherwise, this constant will be very small, but they are all there. But the answer is that no, they don't have a clean geometrical meaning if they are not gluons, except that when we go beyond MHV and consider NMHV and we have a super loop where we also insert other fields, then it's possible to also give a more geometrical meaning to the insertions of fermions. But not scalars. I think scalars don't have a nice geometrical meaning. I think. More questions? Okay, so let's have coffee and Sherman. Let's have coffee and meet one. Let's thank me. Very good. When do we come back?
This is too hard.
Okay, we come back at 50. Typically what people do here, they also consider some kind of effect. They consider the following.